So, in the first half of class today, we're going to be covering classification and regression trees, which are also known as decision trees. And the objectives for the first half of class, and this part might spill over into the afternoon as well, is to, first of all, start with looking at a decision tree and interpreting the output of the decision tree fitting process, the decision tree models, understanding the output of it. And I think this is the easiest way to understand sort of the motivation behind it and also how they're made, is to start with the output. And then we're going to talk about how the algorithm actually works, how the decision trees are created. So this, both our morning and afternoon session are going to be a little bit more conceptual than we have been in the past. There's going to definitely be code. I created lots of code examples, but of all the classes we've covered so far, this is definitely going to be one of the more conceptual ones. So with that being said, I'm seeing some people really excited by that and some people like, oh no, theory. So if it helps you, feel free to take notes. If that helps you stay engaged, whatever works for you. Then we're going to go through code examples of predicting using the Titanic data set, which is an actual Kaggle competition. And we're going to create a decision tree visualization. And we're going to talk about how do you tune a decision tree. What are the different parameters you have control over to dictate sort of what the output is going to be and how well you're going to fit the tree. Lastly, we'll talk about the strengths and weaknesses of the decision trees. Just a note on the nomenclature used. When I say decision tree, I'm referring to classification or regression trees, and I'm using these terms interchangeably. Right off the bat, in the name of classification or regression tree, you can sort of probably guess. Decision trees are tools or techniques that can be used on classification and on regression problems. And once you understand how they work for one kind of those problems, extending it to another problem is very easy, both conceptually in terms of understanding how the algorithm is actually fitting the tree, as well as in terms of the syntax used to create it. So our examples today are going to be classification examples, but I feel like I'm going to be teaching you regression just by the very, very fact that it is so similar to classification in terms of how these trees are actually fit. So what are decision trees? Decision trees are a supervised machine learning technique that can be used on regression or classification problems. The big draw, and I think probably what makes decision trees unique over all the other models we've explored so far, is that decision trees are something called a white box model. They're very transparent. They can be understood in terms of Boolean logic, in terms of the output of the decision tree, and you can visualize it. That fact alone, I think, makes the decision tree very unique. You can visualize it. Now, why is that? Why do I draw attention to that? Well, when I started my journey into the world, the wild, wild west of data science, armed with a little more than basic, simple linear regression, the decision tree was one of the first models that I created. Of everything that we've gone over this class, this is one of the first techniques that I used and I applied for one of my clients. And what made this such a great technique for that situation is a lot of times, depending on who you're interacting with, this wouldn't be true for in all of your cases, but depending on who you're interacting with, you may be working with people that don't have backgrounds in data science. And so what the decision tree gives you is a tool that you can easily explain and communicate to people without a technical background. Because anyone who understands basic logic, which is relatively straightforward, can understand the output of a decision tree. And so I was able to take this model that I created, explain it to my managers, my senior managers, none of whom had data science backgrounds, technical backgrounds, my senior executive clients, people with 40 years of experience in industry, but very little by way of statistics and computer science background. And this helped me to pivot in my career from being a business analyst, business technology analyst, to being somebody who's doing data science. And so that's that's a big part of my motivation for sharing this with you and for you understanding it, is if you're trying to get a job as a data scientist, or you're in a job you think has the potential to become more like a data scientist, which I assume most of you would be in one of those two categories, then this is a great way to sort of make that pivot, to enable you to make that transition from a career standpoint. So end of biographical note there. Okay. What's that? The other piece of motivation behind decision trees, as I mentioned, is that while the decision tree in and of itself is not the best in terms of predictive accuracy, we'll talk more about why that is later, it is foundational to learning some very powerful techniques. I've already heard several people mention random forests. I feel like just typing in data science in Google or like on Kaggle, it's almost like you're inevitably going to run into this thing called random forests. And what are random forests? And they've sort of become synonymous with these Kaggle competitions because they're so powerful and they're so easy to use. So if you understand, like nothing you learn from decision trees this morning will be wasted when you apply your random forests. Everything will be used. So it's foundational to understanding some very powerful and exciting techniques. Talk about models that are like high bias, low bias, high variance, low variance. Decision trees without care, cultivation, tender loving care, parameter tuning are prone towards being high variance models. They're prone towards being unstable. What do you mean by high variance? You train it several times, different subsets of the training data, and you get different results. High variance. And that's a weakness and a strength. It's a weakness because it's not good to have high variance models, but it's a strength, and I'll explain why it's a strength later. Okay, so for today's lecture, we're going to be focusing on the CART algorithm. CART stands for Classification and Regression Trees. CART is not the only decision tree, classification, regression tree algorithm out there. There's a couple of them. A couple of them are proprietary, so people don't talk about them as much. A couple of them involve some more advanced statistical techniques, so people don't talk about them as much. A couple of them are more computationally expensive, so they don't talk about them as much. This is by far the most popular decision tree implementation. I believe it's the only one that is implemented in scikit-learn, so that tells you something in and of itself. Clustering, scikit-learn has implemented like 8 different clustering techniques, and actually Keynes was the most popular, so that's why we went over that one. This is the only decision tree technique implemented in scikit-learn, so that tells you sort of how it's viewed in industry. So like I said, I think the best place to start when describing how a decision tree works, what it is, strengths and weaknesses, all that good stuff, is actually just look at a decision tree and interpret it. And then let that sort of lead and guide our discussion, the questions we ask, and our explanation of it. So what I've given you here is a very, very beautiful decision tree, classification and regression tree. I'm just going to call them decision trees, that's easier to say. So decision tree of the Titanic. I said we're going to be using the Titanic data set today. So what the decision tree shows, there's different components, are the nodes. And these nodes are the logical splits that make up the decision tree. Sometimes they're called leaves. And each node is associated with a single attribute of a passenger on the Titanic. So in your data set, it's a single column. It's a single variable. So at the top of the tree, you see gender. And you see male going off to the left and female going off to the right. And you see several of these. You see one for class, you see one for age, you see one for siblings. And at the end, you see what are called terminal nodes, each with 2 numbers. The first number, the percentage, is the response variable. Okay, so in the case of the Titanic, what would the response variable be? Survival. So this 67% corresponds to 67% survival. Okay? That's the first number. And you see that in all of these, what we're going to call terminal nodes. So what does this mean? This means that if you follow the logic, you can look at the survivability of people, of observations that share the properties defined by that combination of logic. I was sort of a mouthful, so let me show a concrete example. So this node right here, what do we know about the people in this node based on this chart? What do we know? What gender are they? Female. What age are they? You don't know. What class are they? First and second class. So putting it all together, females in the first and second class have a survival rate of 94%. Okay? So let's go down to a different one. This node here, male or female? Age, greater than 37, and then class, third. And so what this is saying is that elderly women in the third class, unfortunately, had a 0% survival rate. Okay? The number below it is just the sample size in each of these nodes. There were 8 women in this data set that met that criteria. There are no men in this subset. There are no first and second class passengers. There are no young women in this subset. Just older. Okay. So, given that question, should these percentages all add up to 100%? No. It's purely the survival. It's just the survival rate. It's the percentage ones. Out of 12 ones, 67% of them. Out of 12 people, 67% of them survived. Out of 317 people, 11% of them survived. Okay? Now, what are you supposed to take away from this kind of diagram? The first thing is just trying to understand what is the relationship between the properties in my data set and the response variable that I'm trying to predict, that I'm trying to understand, I'm interested in, survivability. So what is, for second and third class passengers that were male, what is the relationship of age from this diagram alone on survivability? What is the impact of age? You should be looking at this section. Second and third class men, what is the relationship age and survivability? Yeah, you could say younger survive more, or you could just say, people less than 4, there were not as many of them. There were only 12 compared to 317 that were greater than 4. But those who were less than 4 had a much higher survival rate than those who were older than 4. Okay? So that is sort of like decision trees 101. Okay? How to interpret the output of a decision tree. And this is the kind of conversation that you might have with your client or whoever it is you're presenting this to. Everything on this diagram can sort of be understood on a basic level just by understanding conditions, logical conditions. And this is the output. Every time you run a decision tree, you're going to get something like this. You're going to get something you can visualize and turn into something like this. Okay. So, what questions, if any, do you have about this diagram and how it was created? Or how to interpret it?
How
Yeah, good question. What would happen if you were to change the cutoffs? Because these are all based on cutoffs. Categorical variables, male, female, there's only one cutoff. Second, these categorical variables, there's a limited number of cutoffs. But something like age, a continuous value, why does it cut off at 4? Why not 5? Why not 10? Why not 20? Why did it pick 4? I'm telling you right now, the algorithm picked 4. I didn't pick 4. The algorithm. How did the algorithm pick 4? Good question. Any other questions? Yeah.
Just the presentation, like why each node is where it is. You could have potentially age cut off at 4, like where gender currently is.
Yeah.
And then have gender.
Yeah.
A node under each.
Yeah. Exactly. Why is gender at the top and then class and then age? Why not have age up here and class down here, or like gender down here and age up here? Like, why this order? For those of you who are familiar with the Titanic data set, tell me this. Is this all the variables they give you in the Titanic data set? No. There's a parent-children variable off the top of my head. I think there's others that come out of the box as well. But there are other variables that are not shown on here. So why aren't they on the diagram? How come they didn't make it? Another question nobody's mentioned so far: why did it stop here? Like, there was 317 data points here. Why did they try to split this further and like go into like siblings? Siblings isn't hasn't been split yet, or maybe age again. Like, there's a ton of maybe there's a lot of variation here. Why did it stop there? What about parents, children? Why is it stopping here? I'm just sort of giving you this and telling you like this is the output. To answer these questions, we'll have to go under the hood and understand on a conceptual level how this decision tree algorithm works. And I guarantee it's not that complicated. It's actually something every one of you here can understand. But it's a very specific process. And understanding the process is essential to be able to interpret the diagram, understand the strengths and weaknesses of the technique, and being able to apply it successfully on your own personal projects. So I'll tell you something. I'll give you a hint, and this will be explained more thoroughly in a moment. But the hint is that nodes that are the way you interpret this, the output, is that nodes that are higher up on the diagram are more important, and nodes that appear more frequently also may be more important. Although I'll caveat that slightly to say that if you have a continuous variable, you're more likely to see it more often because there's more splitting opportunities. There's more places you can split it. If age, gender appears to be more important than age because it's higher up, but I wouldn't say age is more important than gender because age appears 1, 2, 3, 4, 5 times and gender appears once. Because you can only split once. After you split, there's no more. It won't ever appear again. So, all right. So, any questions about the interpretation before we get into understanding how this actually is created? Yeah?
Is there only 2-way splits or can you have 3-way splits?
Good question. 2-way splits are the most fastest thing to do. You'll see why in just a moment. With CART, which is the algorithm that this is the output of, CART is only 2-way splits. But there are other techniques that allow for different splits, like 3-way splits. But CART is only 2-way. Good question. Any other questions? Okay. All right, how the algorithm creates the decision tree. So here's my brief introduction to the decision tree. So the goal is to try to understand the characteristics of passengers that are associated with survival or lack thereof. Just generally, the attributes associated with the response variable, explanatory features, and the way this works, and just on a very general, basic level, is that different variables are evaluated. Different splits within different variables are evaluated. And so the algorithm will look at different combinations and will say, which split gives me the most explanatory power in terms of explaining whether the response variable that I have. So what does that mean? What it means is the algorithm is trying to find the feature that will best separate the two classes. That will best separate between survivor and not lack of survival. Spam or ham. Cancer or no cancer. It's trying to separate these two classes, finding the features that do that best. So here's an example where you have, let's say this is the algorithm. You're the algorithm for a moment, and you look at gender, and when you split it along gender, you get, this is a toy example with only 25 data points, and you split it along gender, and then you see the males have a 13% survivability, and the females have an 80% survivability. Say, okay, let's try siblings. Well, let's try siblings at less than 1, so no siblings, or at least 1 sibling. And here you have 42% survivability with at least 1 sibling, and 39% with no siblings. And you do the same thing with class. And you do the third class in one group, and then first and second class in the other group. And you get 23% and 15%. If you were putting your self in the shoes of the algorithm, which of these variables would you select as being the most informative, at doing the best job of providing information, explanatory information about who survives and who doesn't survive? Gender? Gender? Yeah? Okay. Exactly. In this case, the algorithm would pick gender. It's because you see there's this big discrepancy between these two. Here, it seems like it's pretty equal. Here, there's a discrepancy, but it's not as big as this one. So this one provides the greatest separation between the classes, and it would choose gender in this case.
How much does it weigh in the sample size?
Good question. Good question. It takes into account sample size. The metric used, and we'll go over the metric in just a moment, you'll see it does take into account sample size. So if you were to have 100% survivability, let's say you were to have an outlier, and you had age, and there was one passenger who was 60, 70 years old, and he didn't make it, unfortunately. And just one person, and they were to make the split there, and you got 400 data points in one node, and then 1 data point in the other node. And you have a good separation there, because you have the null survival rate in one node, and then you have 0% survival rate in the other node. So it's like a big separation. That would not be evaluated as a good split, because you only have 1 data point. So the splitting is weighted based off of how many data points are in each node. I'll see that in just a moment. I know this is kind of conceptual. I tried to warn you. This is going to be a little bit more of a conceptual start to our day. But I think that it will pay off in terms of understanding this. So, any questions about this so far? Yes.
Are these just random numbers just for?
Yes, they're just random.
They're obviously more than.
Yes. Yeah. This is just numbers. Of course, we're going to do some calculations by hand, just to make it easy. Yep. So the question is raised. You guys were able to tell this just visually. Yeah, this is the best one, obviously. But how do you deal with cases where you have different? Here we are sort of splitting down the middle in terms of sample size each time. But how do you deal with cases where you have how do you actually determine this in a quantitative? What is the quantitative measure for evaluating this? There are a couple of different ways of doing this. The most commonly used metric for evaluating separation or homogeneity of classes would be something called the Gini coefficient, or the Gini index. And this measures something that I often hear referred to as purity, which just means you know, how homogeneous within a particular node, how homogeneous is it? How similar is it? If it's all survivals, then it's very pure, it's very homogeneous, and everybody has the same class. If it's 50-50, then it's like maximum heterogeneity. It's maximum impurity, if you want to call it that. Because equal is perfect balance of classes. So this Gini index is what's used to evaluate these different splits. So how does this work? As I mentioned, well, let me just briefly go over what these terms mean. So what you do is you say 1 minus the proportion of one class squared minus the proportion of the other class squared. It's a very simple calculation, and it's a number that ranges from 0 to 0.5. And 0 indicates perfect separation between classes, and 1 indicates, or 0.5 indicates a perfect balance between classes. So, the way that and we'll go over an example of that in just a moment so you can see the computation worked out, but the way that this works is that, just giving a very broad overview of the way this algorithm works, is that you calculate the purity of the data before performing any splits. And you say, what is the balance of classes? You know, on the Titanic, the null survival rate, I think, is like 40%, like 38%. So like, based on a 38% split, what is the Gini coefficient for that? It's not going to be 0, but it's not going to be 0.5, but it's going to be a little lower than 0.5. Then you select a candidate split. So you select gender. You calculate the purity of the data after the split. And then you repeat that for all variables. And then you choose the variable with the greatest increase in purity. The greatest increase in purity after the split occurs. As measured by this Gini index. And then you repeat for each split, either until you run out of data points or you meet some stopping criteria. And there's different kinds of ways to stop the decision tree from splitting. We'll go over those. We'll go over those in the code. But one way to say it is if your node has, you know, less than 10 data points, don't split it anymore. Or if the node goes down 5 levels, the tree goes down 5 levels, don't split it anymore. I don't want anything longer than that. We'll go over some examples of different stopping criteria, but this is the basic process. Calculate the purity of the data, select a candidate split, so a candidate variable, calculate the purity of the data after the split, repeat for all variables, and then choose the candidate with the best increase in purity. Okay? It's the best decrease in Gini index. So an example. So based on the formula that I showed, what would the Gini index, and I'm going to have you guys work this out. You can just work this out individually. What would the Gini index for this data set be? There's no splitting has occurred. We just have 2 classes, we got all these explanatory variables, and we haven't selected anything. We're just calculating the base survival rate, the base Gini index. So take a minute and try to work out what this is. Again, the Gini index is, you guys, right over here. The Gini index is equal to 1 minus the sum of the proportion in each class squared. And this is I equals 1, the number of classes. So this would just be 2. So you're going to have 1 minus the proportion of survival squared the proportion of not survival squared. So go ahead and just work that out real quick. Just take a minute. There we go. All right, let's go through the answer. And you can see the formula here as well as the actual values. It's 1 minus 10 over 25 squared minus 15 over 25 squared. This is 0.48. Remember I said the maximum impurity, which results when you have a perfect balance between both classes, is 0.5. So you can see it's almost 0.5 because you have 10 and 15. You've got a pretty equal representation from both survivors and fatalities. So that was the original Gini index. Any questions about this? Any questions at all? Okay. So then you select a candidate split. Let's select the gender example. So after splitting on the gender, we've got 15 men and 10 women. Of the 10 women, 80% of them survived. Of the 15 men, 13% of them survived. What does that work out to be? Well, you see the values here. Of the men, 2 survived, 13 died. And then you calculate the Gini index for each of these 2 populations. And you see the Gini index for the males, the left side of the split, is 0.23. The Gini index for the females is 0.32. Okay? So I just calculated the Gini index for each of those nodes. Then I combine them into a single Gini index weighted by, instead of just taking the average, I take the weighted average, weighting by the number of points in each node. Weighted by the number of males and the number of females. That's all this is. 0.23, you'll remember, that's the Gini index for the males. 0.32, the Gini index for the females. And these are just the relative number of points in each node of males and females. And so then you get this Gini index, which represents the Gini index after the split. So now you have a Gini index before the split and a Gini index after the split. And the increase in purity, the increase in homogeneity, and when I say homogeneity or purity, I'm talking about the classes. That sounded so horrible. The increase in response variable is just the difference between the Gini coefficient before and after. So in this case, it would just be 0.48 minus 0.27. So what you do is, going back to our original our example, we had the 3 variables, gender, siblings, and class. And we do this calculation of the Gini coefficient for each one. I won't make you guys do that. And you see that the Gini coefficient after splitting for the siblings was 0.27. After the gender was 0.27. After the siblings was 0.48. So it doesn't seem to be much of an improvement there at all. And after the class was 0.42, which is an improvement. It's lower than before, but it's not as low as the one for gender. And so that's how the metric works to actually select this gender variable as being the best split.
So it's the greatest distance away from 0.5 of the ones that you're comparing?
It's the lowest one. Which is also the greatest distance from 0.5. I know there's a lot of sort of conceptual, computational information. Any questions about that? Yes, Nan.
So the Gini coefficient is. Are there other?
Sorry, what's that?
The Gini coefficient is for split.
Yes.
Are there other coefficients that are also used in production?
Good question. Yes, there are. There's another coefficient called entropy. That is probably the most popular other one that's used. There's a couple other ones as well, but Gini and entropy will be the 2 most common ones. I'll let you look up entropy, the computation for that as well, because I don't want to overload you guys with computations. But it's very similar. And in my experience fitting decision trees, switching out the criterion doesn't make a lot of practical difference in terms of the resulting tree. It's a number that ranges from, it's a measure of purity again. It ranges from 0 to 1 instead of 0 to 0.5. But, the same interpretation holds. 0 is, perfect separation, and 1 is like perfect representation, equal representation.
I bring that up just because in scikit-learn,
Yep.
there are only two options of splitting criteria. It's Gini and entropy. And I think it does default to Gini.
Mm-hmm. Yep, it does. Yep.
Yeah, so it's just so you know there are other ways of doing it.
Yep. And the curve looks very similar to this.
So is there a chance of falling to the right of the 0.5? Having like an example where you're above 0.5 in your Gini score?
No, and here's how you can know this. If you look at this, let's say we had like 10 and 10 here. What you would get is 1 minus 10 over 20, which is 0.5, squared, 0.25. So the maximum you could get would be when you have equal representation, so 0.5 each. So you're going to have 0.5 here, 0.5 here, which is 1 minus 0.25 minus 0.25, which is 0.5. You never have more than 0.5. And then the maximum, if you have no, like if everyone survives, then you would have I just lost my place. What was I saying? If you have, oh, sorry, I'm so sorry. Okay, I just had a complete meltdown there. So what if you have perfect separation? Basically, everybody survives, everybody dies. Then you're going to have the same, so you're going to have, let's say everybody survives, and you have 25 data points. 25 over 25 is going to be 1. 1 squared is 1. So it's 1 minus 1, which is 0. And then you're going to have 0 over 1, or 0 here. So 0. So 1 minus 1 is 0. So that's sort of the intuition you have how this is working. Sorry. I was like, what's going on? Need some more coffee, maybe. Does that make sense? Hopefully that wasn't confusing. It was helpful. But yeah, just range from 0 to 0.5. Entropy goes from 0 to 1, I believe. But it shouldn't affect the output too much. I just want you to understand sort of at a procedural level how this is working. The specifics of the calculation, you could just look up on the internet. But at a procedural level, how is this working, step by step? There's also, we'll get into more details of this when we get into the documentation for the everything. All right. Okay, so any questions about any of that? I know that was a lot of steps, and yeah.
Is it accurate to say for the first split, it's just going to look at all the variables and find the one that's closest to 0.5 Gini?
It would be accurate to say, so look at all the variables and the splitting combinations, and it's going to find the one that is furthest from 0.5, closest to 0. After, because you want to minimize your Gini index. The 0 indicates that you have separation. You have everything's in one, versus another.
Is that the first level down, or when it decides?
Every time. So this process that we went through, it would theoretically just be repeated over and over and over again until you run out of data points to split on. If you only have one data point here before the split, you can't split one data point. It's a binary event. And, this one would be repeated again because once you make a split in one direction, everybody on that side of the tree is going to be, either male or female. Yes?
This class where you divided it from 1 to
Good question. So this is arbitrary in the example, just for illustrative purposes, but it would do one of two things. And this is why I was like, should I wait till now or later? But it'll do one of two things. It'll either just choose a random split, like I have here, or maybe 1, 2, 3, or it will try different combinations. And the same thing for continuous variable. It'll do one of the two. It'll either just pick one, and it'll go with that one, and it'll evaluate that one for each variable. You know, for this one, it's only going to be one, but here there's like lots of different ways we can split that one. Lots of different ways we can split this one. And that's actually an option you can specify in the implementation in scikit-learn.
So in the meet,
Yeah.
I was wondering if you choose one class one and two together, or they will have some version.
Yeah, exactly. So there's an argument, and I'll remind you of this when we go over the documentation. But it's an argument that says you can use best or you can use random, and so best will look at like all combinations, and then random will just choose one and evaluate that one. But I'll show you that part of the documentation when we get to it. Yeah, good question. But generally, when people talk about decision trees, you're looking at like all the possible combinations of variables and splits within variables. That was sort of a. By the end of this class, I'm telling you guys are going to understand decision trees so well.
More than the average person.
Definitely more than the average. Okay, so any questions about any of this? Any additional questions? Making sense?
I have a question.
Yeah.
Is there ever a time where you don't want to split it the best? That was a bad word.
Yes.
Okay, yeah.
Yes. Absolutely.
When?
There would be two. So part of this is getting into ensemble. Actually, ensemble would be one of the reasons you wouldn't want to split the best. And actually, we'll get into that in the random course why it is. The other reason, just a practical reason, I don't know how legitimate this is, but if you've got a huge data set and your like decision tree is taking a long time to fit, you know, or you're doing multiple decision trees, you're tuning, you might want to make more efficient, and you want to choose the best. It is your random one. So challenge exercise for you guys. If you want to, you know, when you take the sum, the homework assignment is based on decision trees, ensemble, and the Titanic data set, and building upon what we do in class. If you want to, try out some of the different parameters and say, like, you know, the reason this parameter isn't what I think is because it'll make it faster. Does it make it faster? Kind of. But the more important reason is something we'll cover in the second half of class. Yeah. Other questions? Okay. So I think let's see here. All right. So up next, we are going to get into code. We're going to implement the decision tree algorithm on the Titanic data set in scikit-learn. So get excited for that. I'm going to create a decision tree visualization. There's actually a special package you need to use to create this decision tree visualization. It's a little complicated to get set up. I'll point you in the right direction for creating these on your own and show you some different options for creating them outside of Python. We're going to do some tuning and talk about some of these parameters that you can tune across and how that impacts the fit of your decision tree. And then finally, we'll wrap up with strengths and weaknesses of the decision tree. As a start to this, there's going to be a little bit of an interactive component where you guys do some coding on your own. But before doing all this, I've been talking to you guys for a long time, lots of information. I see we're coming up on 11:30, so let's go ahead and take a 10-minute break and then regroup at a little after 11:30, 11:32. All right. Let's get started again. Now we're going to move into the code. That was a lot of concepts, a lot of math, some computations. I tried to make it so it wasn't too mathy, too creepy. So now we're going to get into some code. We're going to implement the decision tree algorithm in Python. And I'm going to show you the syntax for that and all the options, all the great documentation scikit-learn has for that. I'm a big fan of. And but to get started, I thought it would be a good opportunity to sort of refresh some of your own Python chops and start out just sort of as an interactive exercise and have you guys do some things like exploring the data, trying to understand some key trends, pre-processing the data, doing some data conversions and things of the like, since those are such valuable skills to have. So what I did is, if you go ahead and open up 08 classification regression trees.py, there's another file in there called 08 classification regression trees.r. Don't open that one. .py, and what you'll see is basically starter code, code to read in packages that you'll need, code to read the data, code to select a subset of the data points. And what you'll see after that is a series of comments, which are instructions for how to explore and pre-process this data so that the data can be ready to go for when we build our decision tree model together. Now, you might have already also noticed the solutions are also in this script. So I put them in there so that it would be easier to go through them together after the fact. But as a challenge to you to test yourselves and to stretch yourselves as budding Python savvy data scientists, try to go ahead and complete the exercise without looking at the solutions first. And then we can go over the solutions together. But the comments, I think, are pretty straightforward. I'll just go over them really quick. Basically, you're going to read in the data, which I already have code for, select a subset of data, check for missing values in all of the columns of data that you have, convert all values to numeric to make it play nice with the scikit-learn functionality. Look for, if you find any missing values, which hint, hint, you will find some missing values, fill in the missing values. And for now, you can just use the average values for those columns, or the most frequent values for those columns, and use that to fill in the missing values. And then I want you to take some time to explore the data. And I don't really give you too much specific information here because I want to sort of simulate what you would be doing on your own project. You hopefully have learned a lot about data exploration in Python through everything you've done so far on your own project. And so take some of those things you've learned and try out some different ideas. Try exploring what is the impact of gender on survival rate and things of that nature. And then lastly, you're going to do some feature engineering, and I've asked you to create a proxy variable representing whether the spouse was on board or not. Now, I haven't really told you much about the data fields. Some of you may be familiar with it. So for those of you who aren't, you know how to read in data and explore it to see what the data fields are, what kinds of data types there are. So I won't give you too much information there, but I will say that one of the variables stands for spouse and sibling. And it's a count of spouse and siblings. And so what I'm asking you to do is do some feature engineering. Try to see if you can create a proxy variable that separates out just the spouse part. Because maybe spouse has a different impact than siblings. And maybe that would be something you would be interested in doing if this was your own data, if this is your own competition. So this is, again, it's going to require a little bit of creativity. Think about, okay, I've got this numeric feature that shows me a count of how many siblings and spouses on board, and I've got these other variables. Is there any way to combine the information I have and try to proxy back out just the spouse? This is what's featuring. This is what separates the top tagglers from everyone else. This is what it is, according to the president. This is not my opinion. This is according to the president of the organization. Okay? So let's take some time and go ahead and get started with that. Let's go ahead and work in groups for this. But each person should do it on their own computer. Let's go ahead and work in groups. So I'll just go ahead and split you up into twos. Actually, why don't you guys be working the same team since you're all on the table together. And you two, if I have you guys work together, and you two work together. And then you two work together, and you two work together, and you two work together. You have no spouse. I'm not your spouse. You are not your partner. You are each other. All right. I hope you guys had some good time to exercise your Python muscles. Go over the solutions together, and that will bring us right up to the code for decision trees, which will start right before lunch, and we'll take a lunch break at 1. Okay, so the first task was to check for missing values in all columns. The very simple way of doing this, which I use a lot. Can you guys see my code in the back, Sung and Lena? You guys see okay, or do you want me to make it bigger? Okay. Fine? Okay. After the class is fine. Okay. So a very common command that I use quite often is just summing up all the null values by column, just to check to see if there are any null values. Let me read in the data so you can start from fresh together. I saw a lot of you got this. D is null. Just D is null by itself. Just generates for every column. It just looks at all the columns. It checks whether anyone is null or not. As a couple of you pointed out, nulls are represented in Python. When it reads the CSV file, there's nothing there. It represents an NaN value, which is different than just specifying like a string that says string NaN. It's like a specific thing that is in response to missing cell values, and so that's what that checks for. And then sum just treats all the trues as 1s and all the falses as 0s. And so right here it's saying the survive column didn't have any null values. The age column had 177 null values. Okay. The second thing that I did, I'll just break it down. It's sort of a lengthy piece of code. I'll just break it down piece by piece. What I did was I did a group by statement, and I wanted to see, are these missing values like of a particular kind of passenger? Or is it just like equally distributed across all passengers? Why not, right? So I did a group by statement here, group by sex and passenger class, and I just looked at the age column, again, because I identified the age column as the only column with missing values, and I just did an apply, basically what I did before, but just in a group by apply method. And so this is doing the same thing as before, except it's just doing it on the age column, and it's splitting it up by these categorical variables that I happen to have handily in my data set. And this is the output. You see the male and female, and you see the first, second, and third class. And I thought I saw something here, but I wasn't quite sure. What I thought I saw was, people in the third class are the ones that are less likely to have their age, that the age is missing in the third class. But I wasn't quite sure, because it could just be, there's a lot more people in the third class, and so I wanted to normalize that by the count of how many people were in each class. So what I did is basically create another group by statement that did a count of how many people were in each class. And you can see there that it has the same index, the sex and p-class index. And so because it has the same index, and pandas is awesome and vectorizes this stuff, you can just divide through the one group by statement by the other group by statement, and you get you get a view of how many missing values you have, but it's normalized. So you see that 40% of the missing values are third class females, and 37% are third class males. So that's just something that I thought was interesting, because later on when we're building a model, we want to know what is it about these people that it's making. First of all, what can we know just out of the box based on this decision tree algorithm about characteristics of people that are more likely to survive and characteristics of people that are more likely to die? That's like step one. Step one is doing that. Step two, or maybe it's step two, exploratory is first, and then step two is that. Step three is, okay, of all the ones that it's getting wrong, of all the false negative, and false positives, why is it getting them wrong? What are the characteristics of the false positives that make them different from the true positives? And so having this kind of information about where the missing values are can give you some, it's just sort of context for interpreting the output of your model later on, where you're trying to tune it. So that's sort of the rationale for that. For converting values to numeric, I just used an mp.where command. I saw some of you guys experimenting with some different techniques here. There's many ways to skin this particular cat, but that's what I chose. Excuse me. Sorry, what's that? Yeah. So this is again just a refresher. Just like pretty much every kind of this kind of statement you'll see like in R and Excel and other programming languages. The first part is the condition. The second part is that the condition returns true, and the third part is the condition returns false. There's a condition, true, false. Condition, true, false. Yes, exactly like that. Yep. Exactly. Okay, so that is that. Age, filling in the missing values. This is definitely not a very sophisticated way of filling in missing values, but it'll do the trick for now. It'll get us some results that we can interpret and we can improve upon later on. One of the quotes that I get the most mileage out of all quotes by all statisticians ever, is a quote by, I think it was Tukey or maybe it was Fisher. I can't remember. Maybe you can tell me. All models are wrong. Some models are useful. You get so much mileage out of that quote. But basically, let's try something now. Let's just fill it in, interpolate a very simple interpolation so we can get some results to interpret. That's what the focus of the class is. And then we can go back later and we can make this more sophisticated later on. I've seen, I've seen graduate level courses, like semester long courses devoted just to the topic of interpolation. So this is like a really, it's a really big topic, but we'll just make it really simple for right now. And as a homework assignment, if you would like to take on the challenge, of the homework assignment, then one of the questions is come up with a more sophisticated way of doing this. But this is just using very simple, the dot fill NA method, which is a method for series, and or data frames, and it's just you specify as an argument what you want to fill NA with. I want to fill NA with the mean. So I've got the mean value here. This is just a single integer value. 29.699, and you see what happens when you just run that. It just here's one that was a missing value before, the fifth element. Fifth element was NaN, and now we're going to fill it in with this mean value. Note that I'm filling in an integer with a float, and this works. Who knew?
Can you comment on how much that skews your data if you have a ton of NAs versus removing them?
Can I comment? So how much it skews the data?
Yeah.
How do you mean?
The average of everything and you have a lot of NAs.
Yeah.
Change the actual.
Yeah, I mean, of course. Yeah. No, your intuition is right on. If you have 70% of your data in your age column is NA and filled in with the mean, you're not going to be explaining anything, because the whole point of having these explanatory variables is you want to explain. You want to explain the variance in the outputs. You want to explain. So if everything is if it's just a constant, then it's not going to explain anything. I'm sure there are rules of thumb out there. Like if you take the graduate level class, they might have a couple for you. But I think it would be. I'm not aware of any. I'm typically pretty skeptical about just having these arbitrary rules of thumb. I don't know, Sinan, have you heard anything about rules of thumb for if you have this many missing values, then discard the I think it sort of depends on the size of your data set too. Yeah. One thing you should do, one general practice you should do is if you have missing values, you always want to be aware that you're not creating by subset, because you want to have, this is getting to the statistics part of it. Statistics is all about, understanding populations. That's what it's all about, is populations. And you want to be able to make inferences about populations. And you want to have confidence that you're you're generating a sample that is representative of the population itself. So one thing to do to make sure you're not biasing the result by let's say if you were to leave out the NA values, is to look at the characteristics of. We'll do this. We can do this in just a moment. Actually, we just did it. Look at the characteristics of where are the missing values. The missing values are more likely to be in the third class, passengers. So it's not something that's something to be cognizant of. It's not necessarily a deal breaker, but it's something to say. Well, if you just remove the missing values from the data set, you're not going to have a lot of the third class passengers. So you want to know where these missing values lie. Because you might, unwittingly, by just removing those NA values, you might unwittingly be removing a huge subset of your sample you're trying to use to make inferences on this.
As an example, one of the data sets during .csv with the working for drinking spirits, wine, and beer. We did that, right?
Yeah, we did.
If you remember, if you just read the CSV and then drop NA, what happened? Because there is an error in the importing of the CSV. Because all the North American, in the continents, all the North American continents or countries were labeled as NA for North America. So Pandas read that in as none. So when you drop NA, you actually remove all the North American countries. So there are times where just blindly removing NAs, you're just completely eliminating something. Because that column had the phrase NA and it's not applicable or not, it means something else.
Yeah.
So it's really, it's a very bad habit to just drop NA automatically.
Yeah.
Better just look where they are and
Yeah.
see why.
Yeah. And some techniques do a better job of handling missing. Some techniques will just run error when you deal with missing values. And some techniques will be a little bit more robust to having missing values, but you should always be. It's never something to just go into blindly. It's always something where you should think about, okay, how is this going to affect my ability to interpret the results?
If you do have an NA with multiple columns where it does have data in the other columns, the standard practice is to remove full row.
No, that's not standard.
No.
That's not standard.
No.
You could do it if you wanted to. Maybe if you have 100 million data points and you have a couple of them that have missing values, maybe you'll just remove those values. But that would be something where it would be dependent on a portion of missing values. You might want to do that. But, interpolation is pretty important. It's a pretty important topic, I'd say, for sure. And understanding how this is affecting your sample is pretty important. So, good questions. The next task was to explore the data to identify trends in the characteristics of survivors or people who were not survivors. The first thing that you're going to want to be aware of when you do a classification problem, or just any kind of classification problem, whether it's binary, dichotomous, or multinomial, is just to understand what's the null rate. What is the how many people are in each class? Just something that's good to know. Here we see there's 342 survivors and 549 were not survivors. So 1 means survive in this particular case. And if you're wondering how I know all this information, there's a data dictionary on the Kaggle website that goes over all this stuff. But anyways, so you got somewhat balanced set, but there definitely are more people who died than people who lived, unfortunately. Another way of looking at the same information is just to take the average. The average. And this is a way of just showing what the survival rate is. So taking the average, bunch of zeros and ones. This is the same thing because it's represented as zeros and ones. It's the same thing as just taking what is the survival rate? What is the null survival rate? Just to illustrate that point. Is that what's giving me? This divided by D dot shape there we go.
If you have a series, just doing bracket notation, like doing slicer, like 0, 1, in this case, or in case we have a series, it will just return that actual value. Right?
Yeah, just returning the first value. Yeah. Yeah. Probably I should have used .iloc. That would have been the Pythonic way to do it. I was just proving the point. So does that make sense? This is same thing, average, same thing as just the survival rate. A little bit of a subtle point, but okay. So survival rate for everyone. So now let's start looking at some of these metrics that we have about the passengers. Let's do, and this is one of the this is one of the primary uses of split apply combine. Back when the first day or second day of class, we were talking about pandas. Maybe it was third day. Talking about pandas, and I said there's 2 uses for split apply combine. The first use is for exploratory data analysis. The second use is for data transformations. I mean, they're really the same thing, but you can think about the application as being slightly different. So here we use split apply combine as an exploratory tool. I think split apply combine is one of my favorite parts about pandas doing data analysis in Python. I think it's very intuitive. And the, you're like, okay, decide if you say so. Once you get used to it, I think it's intuitive. And so here we use split apply combine just to split across categorical attributes in our data and evaluate the survival rate across different combinations of categorical variables in our data set. This is just one way of doing exploratory data analysis. I thought this was insightful. This data set, because we had categorical variables that happen to be insightful. So I'm going to look at split apply combine, the sex variable, whether they survived, the mean. The same as before, I'm just splitting it by gender. Ooh, this is interesting. So do you remember what 1 and 0 represent? That's 1 is the female and 0 is the male. And it's survival rates. There's that Gini split, that logical split that we were talking about earlier. Females have a much higher survival rate than males do. So that looks like it could be that's a very informative variable. Now I didn't get that by luck. That was after several iterations of trying this, but you might have guesses about what you think might be the case, and you can test it out and iterate. So here I'm going to do the same thing by class. Ooh, another winner. Another winner. First, a winner in the sense of it gives us information about survivability, not winner in an ethical sense. In an ethical sense, this is a loser. This is horrible. This is something that Titanic, company that manages Titanic, vehemently denied. But data proved them wrong. People in first class were obviously given deference over people in third class tickets. That's bad, but it's a good variable. It helps us predict. So I'm trying to walk this fine line of talking about the fitting process and talking about the actual historical event. But in terms of the fitting process, this would be an informative variable. First class passengers, much more likely. Well, what if there's an interaction between the passenger class and the gender? Let's look at both of them together. Doing that in split apply combine is as simple as passing a list of the column names, the string column names you want to apply across. So I'm going to pass the list of the two variables we just mentioned. And you can see, again, this is a reminder, 0 is male. So the male first class passengers. So a way to think about this is the trend we saw is that, first class, second class, third class, there was an order there. Does that order hold true across genders? Is there differences across genders? Well, here you look at the males, and you see that, male first class passengers had a lot higher than second and third, but second and third look like they're pretty similar. 13% and 15%, that might not be different. Look at females. Is there a difference here? Well, first and second class passengers are both in the 90s, but third class passengers at 50%. So here, for the males, the distinction seems to be more of the first versus the second and third, and the females, the distinction seems to be the first and second versus the third. Do you see that in the data? First and second look very similar for the females. Second and third look very similar for males. Yes?
Why would the third class rivalry be exactly 10%?
Why? It just worked out that way. Yeah. Unless somebody Kaggle tampered with the data that I'm not aware of. Yeah, I just downloaded this from Kaggle. Another thing you might want to be interested in is, well, how many people are in each of these groups? That'll be another former thing to say, thing to do. And you could do that as well. We won't do that now for time. Any questions about this so far? These are the kinds of things you should be thinking about your own project when you've got categorical variables and you've got, a continuous output or not. A continuous output or a categorical output. This is one way, this is one tool you can use. I think a very useful tool. You don't need a data visualization for this. This is six data points. You don't need a data visualization. You can just look at the data. It's just for exploring, trying to understand. This is a huge, huge part of the process. Any questions about any of this stuff? Okay. All right, so last but not least, you were asked to create a proxy variable whether the spouse was on board. This is the feature engineering example. I saw many of you got this. The way that I did this. This is actually I was filling in for DAT 5, which Alex is a member of. By the way, if you guys didn't notice, Alex is joining our class today. He actually works at Deloitte. He is in DAT 5, and he asked to sit into this class. And I was actually doing a similar talk there, and one of the students actually came with this idea for this feature, and so I was like, I'm going to use that in this example. That was I can't remember his name. Anyways, so is the person older than 18? And does this person have at least one sibling and spouse? Obviously, this logic is not airtight. But again, going back to this analogy of all models are wrong, some models are useful. Maybe this will be a useful feature. Maybe not. Can anyone tell me, so I'll just go ahead and run this, show the results. So there's a good amount of people. There's 200 people or so that would have a spouse by this logic. Can anyone tell me? How you would get sibling from this information? How would you get sibling? So we've got spouse. We've got sibling spouse. How would you just get sibling? We've got two variables that are independent of each other.
You could take out age, or you could put the operator in the age logic condition.
Say -1.
Same.
If it's greater, sibling spouse is greater than equal to 2, they automatically have to be siblings. You can't have multiple spouses.
You can have spouse.
So
but you could have one sibling.
Well,
Right.
taking your premise of they can't have multiple spouses, you could have. Could you not have a spouse and a sibling?
Right, that's what I'm saying. So that if it's 2 or higher,
Okay.
then it has to be.
Okay.
Then it's sibling.
Okay.
Sure.
Okay.
Right? Because you can't have 2 spouses, so it's got to be it's either 1 spouse and 1 sibling, or 2 spouses or 2 siblings, right? And then you can do like another subset with one where it's just equal to 1.
Uh huh.
Sibling spouse is equal to just 1. You can say, okay, that and age less than or equal to 18, and maybe you're more likely to hurt children, or more likely to be siblings.
Okay. I'm not sure I followed everything you said, but I think I see where you're going, and I just want to comment on what you guys are saying. Subtracting 1 would not give you siblings, spouses. or subtracting. What was your suggestion, Noah, again? I'm trying to remember.
I was just thinking, like, if your sibling spouse is greater than one,
Okay.
then I mean,
So I think it's pretty.
number of siblings. Right? If it's a spouse and the sibling spouse is greater than one, then you subtract one.
Yeah, you could do that. That would leave out the people who did not have a spouse on board. But I mean, you could easily say, you know, if you want to make these two variables independent of one another, which is what you would want to do, you could just, as Ben said, just flip the inequality here. Just if they have, you know, more than one sibling spouse and they're, you know, and they're less than 18, and you can make it more sophisticated so that, you know, the people who have spouses also can have siblings. So you could add that aspect as well. But
For that time, you could also change the age threshold to like 16.
true, yeah. You could look up what is the average age of a marriage for everyone who was married back in that time. It was a lot younger. Yeah.
We had another idea that if you're looking just at the name variable, that you can at least get the. I'm sorry if you said this. You could look just for MRS string.
Yeah.
And
Yeah.
then that would.
Yeah.
Yeah, you have to link that with if their sibling spouse
Yeah.
is greater than.
Yeah.
It can be married, but their spouse could not be on board.
Yeah.
Or just see their spouse.
Yeah. And so what do you want to represent? Do you want to?
You can search on last names.
Unfortunately, it's not England where there's an actual difference between men if they're married or not. Married.
Oh yeah.
Well, in England, it's master. If you're
Yeah.
not married,
But-
Mr. if you are married.
Isn't it? Well, but they don't report it as.
But there's an embarked thing where they got on from. So for English, they do this like master.
Yeah.
There's
You
so,
could-
that's the thing. There's so
Suffice
much
to
stuff.
say, given the combination of embarked, passenger name, which includes the Mr., Miss, Mrs., the surname information,
I was thinking-
and the
Hold on.
yeah, there's a lot of different ways you could do this. I'm just wanting you guys are starting to think about this and come with ideas of your own. That's awesome. Like that's great. That's what you want to do when you're doing these kinds of projects. You want to have like ideas. You want to come up with lots of ideas. It's never, almost never, about just taking the data as is, running a linear regression, and running a random forest, and just be like, all right.
Evolving.
You know, it's never that way. It's never that way. Like that. First of all, it wouldn't be fun. But second of all, everybody can do it. Anybody can do that. Where you differentiate yourself, where Kaggle competition winners differentiate themselves in their creativity and ability to back out features from the information they're given. And so that name field, that is like ripe with like information. There's so much information. But you gotta use regular expressions and you gotta use, you know, understanding of like how names work and things like that and decide, well, do we want a spouse variable to be true if the person is married but their spouse isn't on board? Or is it only going to be if like, is there going to be a separate variable for like on board, not on board? You know, married, yes or no, then spouse on board, not. These are all kinds of things that you can come with ideas, you can test them, you know, proactively at the front end, or you can run the baseline model and look at what are the false positives, what are the false positives, false negatives, and say, okay, I'm seeing there's a lot of these the false positives are women, and they're younger women. And so let's try to get some information on how we describe these younger women. Anyways, we're right at 1 o'clock. I don't want to keep you guys from your lunch. So let's go ahead and take a break here, and when we come back, we're going to run through the decision tree example. And yeah, have fun.
Lunch?
Yes. Right. Let's start it again. So when we left off, we had gone over, basically this morning, we've gone over a lot. We've gone over characteristics of Kaggle, competition winners. We've gone over ROC, confusion matrix review. We've gone over the motivation for a decision tree, what a decision tree is, how to interpret a decision tree, how a decision tree is created, on a conceptual level. And why that's relevant is that given what you all know about Python, given what you all know about base Python, pandas, NumPy, you could actually create a decision tree algorithm. Given a couple of hours, maybe more than a couple of hours, each and every one of you could actually create this algorithm, a very simple version of it. Because you know everything you need to know. You know all the math, you know all the steps, you understand the process. I'll just give you, if you're following everything. So now, the rest, so if you would like to know what it would look like to do that, I would encourage you to go to the documentation and click on that source link, and you can actually look at the source code for Scikit-Learn Learn Decision Tree, which we're going to be covering next. So before getting back into the code, was there any questions about like the decision tree, just at a conceptual level, or any of the Python that we've covered so far today? No? Okay, cool. We'll jump right into it. So we've just prepared this data set for being used to train a decision tree. And so now I'm going to go through steps that you should be very familiar with by now, splitting the data set into train and test sets. I'm going to convert them back to data frames for convenience. And I'm going to show you the syntax for creating the decision tree. So first of all, the decision tree is coming from the tree package in sklearn. So that was something important at the very top of our script. And now we are using decision tree classifier. And we're just initializing this decision tree with a random state of 1 so that we can get the same results. The decision tree classifier, as you'll note, is only for classification problems. If you wanted to take this and do a regression problem, there's a decision tree regressor that you use. So it's a separate function, but it's still part of this tree package. But that's the main difference there. But anyways, so create ctree object, and then we're going to fit, and the fit takes the x and the y arguments. There's a slightly different way I'm specifying this than I have in the past. That I actually just learned this last week. I didn't know about this. But you can drop a single column, like you can specify a column name, column string name, and just drop that column from your data frame, which is really handy in this case when I have a data frame that has all of my explanatory features and my response feature, and I just want to drop that one. I don't want to type out by hand every single column name, and I don't want to be dependent on knowing the position of the column. I just want to call it by the string. And this is a handy function to know. I just learned it this last week. I thought it was really cool, so I'm using it here. But obviously, this is something that needs to be a data frame form to actually use this. So that drop, and this is, I'll just print it out so you see what that is. This is everything in my data frame except for the survived. And then my y is, of course, whether this survived or not. I'm going to go ahead and run this. What it prints out is basically the default values or any values that you specify. All the arguments. What are the arguments specified as? And so you can see some interesting things here. I won't go into this now. Maybe we'll go into it later if we have time. But just mention, the default criterion, which is the splitting criterion, is the Gini criterion. And then this random state equals 1 is because I set the random state equals to 1. So these default values are the values that you'll get if you don't specify the arguments. You also see the splitter equals best. We were talking about the random splitter versus the best splitter. This is where that argument would be placed. Right now we're just doing splitter equals best, which is the default value. But that was a pretty fast. That was pretty fast. So what I'm going to do now is I'm going to show you how to create the visualization in Python. You're not going to be able to do this. You're going to have to actually download GraphViz, which is a separate package. and we can help you with that if that's something you would like to do. But this is the syntax for creating the graph viz, and this is just something that I pulled straight off of the scikit-learn website. But basically, you go to this graph viz, you may or may not need to add the package to your path, and you might need to restart your computer, and then it involves a little bit of command line finagling, which I'll show you right now. It's this command here. So what I just did is basically create this dot file, and what I'm doing now, so I'll show you where the dot file is. Data, not data, it's in code. So here you see this Titanic dot file that I just created. It's not the easiest thing to look at, but it's a series of labels and splits and number of samples at each split and the Gini difference at each split. There's a lot of information there, and I'm going to convert this to a PDF diagram that will be a little bit more easier to read, hopefully. cd.code. So now I created this PDF file. You see the PDF is there, and you see this is the output. Pretty interpretable, huh? This is actually, I kid you not, this is actually what a lot of diagrams that I look at sometimes look like that are not related to this data science, but just related to documentation for large organizations. But it's a bit of an eyesore. It's a bit difficult to interpret. But the reason for this is that because we didn't specify any stopping criterion, it just kept splitting until there was no more. It couldn't split any further. And so let's just zoom in and see a little bit of this. So here's a split for the siblings and spouses, and it shows the Gini coefficient, and it shows the number of samples in this particular node, and then you have the split here, and then you have here is a terminal node. So for the terminal nodes, it shows how many are in each class. For this, 0 and 15, this corresponds to 0 fatalities and 15 survivors. The number of samples, the Gini coefficient is 0 because you have perfect separation between classes in this particular example. Here you see this is not a terminal node, so you see another splitting criteria, and you see the number of samples here as well. This is a bit difficult to interpret, so what I'm going to do, just to show you a much more interpretable example, is to go back up and to specify a stop criterion for the decision tree. So in addition to random state equals 1, I'm also going to specify max depth equals 3. Max depth equals 3. Max underscore depth equals 3. And I'm going to specify this in the place where I instantiated the object. And I'll go ahead and run this all over again after I've closed out of it. And this is the tree that results from that. So you see a max depth is equal to 3. It doesn't count that first level, but it goes 1, 2, 3. Or maybe this is the 0th level, 0, 1, 2, 3. But this is what the result is, and you see it basically stops splitting. It could continue splitting, like here it could continue splitting, but it doesn't because I specified a stopping criteria. So it doesn't go any further. If this seems a little bit arbitrary, it is. It is arbitrary. I just specified 3 because I wanted something that was a smaller decision tree, and I wanted to be able to look at it and explore it with you all. But the way to read this is actually let me make an even smaller one so it's even easier to read. Let's go with max depth equals 2. And I apologize that you will not be able to recreate this graph right away. You'll need to actually download some additional packages for that. This is one of my least favorite aspects of working with scikit-learn. Anyways, okay, so here's a little bit more of an interpretable diagram. You see a diagram, it's fairly similar to the one that we were talking about at the beginning of class, where you've got the gender on the top, and then you've got age and class also in the diagram represented. The way to interpret this is, so you've got the gender less than 0.5. So less than 0.5 would be, so we have gender of 1 is equal to male, and gender of female and male. I think that was how I specified it. I think it is.
Female is 1, male is 0.
Yeah, female is 1, male is 0. You're correct. So female is 1. So females over here, females who are in the first. So this is 1. So less than 0.5 goes this way. More than 0.5 goes this way. It's not super intuitive, but the way I think about it is that the true, you just follow the direction of this. You can almost think of this as an arrow less than 0.5. So the men are these nodes, and the females are these nodes here. So we got the females, and then we've got the people that are first and second class would be this case. So females in the first and second class, 111 out of 117 of those survive. That's how you interpret this. It's not a very pretty output, I don't think. But it does. Once you get used to sort of interpreting this, you can use this for sort of exploring the relationships in your data. Like I said, I think just from a visual perspective, I think this is one of my least favorite aspects of scikit-learn. Just visualizing these decision trees. So what I wanted to show you briefly was just a couple of different options for visualizing decision trees. And I'll just show you these I'll show you these really briefly, and we'll have to move on, and we can talk about them more another time. R actually has some really robust visualizations for creating classification trees, regression trees, which I've used in the past. I've also used D3 to create tree diagrams. There are some packages in D3 that, for those of you who are familiar with JavaScript, D3 is a JavaScript library. There's a bit of a learning curve involved with both R and D3. If you're not familiar, I just mentioned them to you in case you're interested in learning those or you already have some background in those. What I did want to do, though, was to give you an R script. Basically, everything that I'm doing today in Python pretty much can be done in R, and most of what we do in Python can be done in R. And so what I am going to, I do want to give you this is just sort of a freebie, is an R script that I wrote that creates a classification tree on the same data set in the same way, but it just shows you the different syntax. It shows you the different way of visualizing the output. And both Sinan and I know R, are very, very comfortable with R. And so if you're interested in learning R, we're not covering it in the class. It's not hard. Like no General Assembly uses R anymore for data science. But that being said, if you want to come to our office hours, we're happy to teach you R that way. So here's RStudio. RStudio looks very similar to Spider. There's 4 different sections here. You can change the sections. But you've got a console and you've got an editor, just like in Spider. Console and editor. You've got a help file here, and then you've got this is the variable log in RStudio. And so I'll just run this. I'll just run this real quick to show you what the output from R looks like. this is the plot that I would. This is a very quick plot that you can generate. It's a lot more interpretable than the Python. It shows you much more clearly what different decision points mean. It shows the variable and then the value, male, female, and then at each node shows you the percentage. So females in the first and second class have very high survival rates. Same interpretation between males that are older than 6.5 that are in second or third class have a very low survival rate. This is another way of visualizing it. It's not pretty. This is not something you would present, of course, but it does the trick, and you can understand. It's very interpretable. The other one takes some getting used to. The dot, the graph viz creation, in my opinion, takes some getting used to. The last one I'll show you, which you've already seen actually, is just the D3, which is what I created for this. This is the D3 version. This is the D3 version. I customized this to my heart's content, and this looks much prettier, but it takes some time to actually get in that shape. But if these things are interested in exploring further, I have included some links to in the resources section to learning R, if that's something you're interested in. R is a very valuable skill for data scientists. It's slightly different in some subtle ways from Python. But I also included some links to D3 resources, and specifically creating these kinds of tree models in D3. So not going to cover it in class, we don't have time, but just wanted to throw it out there for your own self-study if that's something that you're interested in. So any questions about it? Any of that? Yeah.
I mean, the class was the D3 one, but on the Python R version,
Mm-hmm.
the class variable was saying greater than 2.5.
Yeah.
It doesn't understand it as a categorical variable. It seems to me like you wouldn't be able to make groupings like this. Like you want to do group 1 and 3 versus 2.
Oh yeah. So good question. So for the R, it does take in categorical variables. So R, one of the data types, you've got your integers and your floats and your strings and your booleans, just as in Python. In addition, in R, you have an additional data type that you don't have in Python called categorical, or factor, is the name of it. And so it's treating this as a factor, male, female, but it's not treating this as a factor. It's treating this as an integer right there. So if you were to specify factor, then you would see these kinds of groupings, just as you see here. You would see like that in Python. So it's just one of those things about Python. Python does not currently support, at least Python 2.7. I don't think Python 3 does, but it does not currently support a factor data type.
So if you wanted to do that, create 3 variables like class first, true or false, class second, true or false.
Yeah, you have to create dummy variables, or in this case, it's ordinal. And so as long as you're okay with the assumption that there's the same distance, or the same difference, like second to first class is the same upgrade as like third to second class, they can just treat it as a nominal variable. But you're right, you're not evaluating these as combinations of factors. Yeah, good point. Yeah.
So for this one, you would interpret, even though that class is not a factor variable, you can still interpret it as 1 and 2, or sorry, 3 is to the left, 1
Yeah.
is to the right.
Yeah.
But what he was saying is if you wanted to specify, break it up into 3 trees, would it know, is there just an argument you can pass in to tell it to split the 3 for non-factor variables, like anything with continuous or as categorical with at least 3 categories, and you say 3.
So when you do the dummy variables, this sort of goes back to our discussion on dummy variables and linear regression. Same topic applies here. What you would do is you would dumbify the data before putting it in the formula. before putting it into the model. And so there's a module called, actually Pandas has limited ability to sort of do that conversion.
Just create dummies.
Just create dummies.
Yeah, we did that last week, right? Just PD.get dummies.
Yeah. Oh yeah, we did do that last week. Yeah. Thanks for reminding me. There's another package that does it even more extensively called Pass. But yeah. So you could do that. What you would do is you would do that, and you'd have, in this case, you'd have 2 dummy variables.
Okay.
And you would pick which ones you want them to be. Do you want them to be second, third, or first, second, or what do you want them to be? But in this case, it sort of makes sense to have them just as a nominal, variable all in the same column because there's a worker to it.
Mm-hmm.
But if you had a non-worker, that would be very less than you do with it.
Mm-hmm. But it wouldn't know to split it. Like you couldn't specify like split each into 3. It's like there's no argument you can pass it. It would obviously
Not within the decision tree implementation. No.
right.
Is that what you're asking about?
Yeah.
Yeah. Yeah. I don't know. Sanan, do you know if Python has any plans? Are you aware of any plans to include a factor data type in?
Not.
Yeah. I'll think about it. This sort of comes back to the difference between R and Python. Python is developed by data scientists for data scientists. It's developed by statisticians for doing statistical data analysis. Python is developed as a general purpose programming language, and the data science, statistics, econometrics, that came later. And it's sort of still being developed. It's not quite as mature maybe in some senses, but the plus side of that is it follows development best practices and has a much more organized development community. But
With R or Python?
Python, yeah. R is it's like a wild west out there. Looking for a package, there's probably 5,000 plus packages for R. And for doing decision trees, I could probably do decision trees 5 different packages in R. And Python it's a one package, and everything is consistent. The documentation is consistent. Doing the iteration, the grid search, and we'll just do that in that. And that's consistent. It's a really nice feature of Python, but
If
there are
if they're both open source, how do they control how do they control that?
How do they control it?
Well, can anybody go and write a package and put it?
I don't know.
It has to be approved by
Anybody could write a package,
Yeah.
but people just don't use it as much. And I think the development community in R is much more fragmented, whereas in Python it's much more cohesive. And what do they do to support that? That's a good question. I don't know.
Depends on the field, right?
Yeah.
I guess who's developing modules for what purposes?
Mm-hmm.
Because I know in R, in some financial modeling, modules are widely accepted and considered to be very reliable.
Yeah.
But maybe not for others, right?
Yeah. Oh, definitely. And the same thing with Python. There's lots of different modules that can do a lot of this stuff as well, but they're not necessarily widely accepted. Yeah. Oh, yeah. I'm not saying that in any way is a diss against R's reliability. R is incredibly reliable. But there's a lot. The question is not, can I do a classification tree in R? It's which package do I choose to do a classification tree in R? So that's a bit of an aside, but I did want to give that to you just because R is a valuable skill, and maybe this could be starter code for you. That's helpful for you. A lot of it is very similar, interacting with data frames. It's very similar interaction between the two. In fact, the data frame concept in Pandas is borrowed from R. The name itself, at least. Anyhow, any other questions about that? Okay. So back to this. All right, we're at 2:30. I'm gonna pick up the pace here. So let's go ahead and evaluate our tree. I'm going to skip over some code here, and I'm going to evaluate the tree another way by looking at the feature importances. And this is an attribute of the data, And so you can just call the attribute by calling feature underscore importances underscore. And what these represent are for every feature in the data set, 1, 2, 3, 4, 5, 6 features in the data set, each one is assigned a feature importance score. And these are based off of the Gini index values. For every time that variable appeared in the tree, it split, there was a decrease in the Gini coefficient. And these values represent what are the average decreasing Gini coefficients for each variable, for every time it appeared, in the tree. So you can think of it as the higher the value, and they're normalized, they're out of 1. But the higher the value, the more important it was. So the second feature is saying it's the most important, and these other 3 features are zeros, which probably means they just didn't show up in the diagram at all. And so, what does that mean? Well, let's go back to our example here. We only had 3 variables up here. We had the gender, we had the age, and we had the class. Only 3 variables, okay? And we have 3 importance scores, and the other 3 are 0. So what do you think these represent? Let's look at our features. And we've got class, sex, age, all of which appear on the diagram. Now we've got siblings, sibling spouses, parents, children, and spouse, which don't appear on the diagram. So what this is saying is that the most important variable in this was sex. And the second most important was class, and the third most important was age. And these other 3 didn't even appear. Seeing some confused stares here. I was curious about how exactly are these calculated? Is it really just an average? And it turns out, yes, it really is just an average. It's very straightforward. If you don't trust me and you want to look at it yourself, don't be offended. You can go to an Excel spreadsheet that I included, calculating cart importance, where I have an example calculation. I have a diagram here. There's the Gini coefficients, number of samples, and then it shows how you derive these values. So if you're curious about understanding all the details of that, I would refer you to that. We're not going to go through it right now. Just suffice to say, these are average Gini scores.
Different results when I do feature affordances. Okay.
I've been changing mine a lot, yeah. If you, that's to be expected. Here's a way of cleaning up the output and making it a little bit more pretty. Just turning it into a data frame. Some code, I'll let you look at that on your own time. So now I'm going to evaluate the accuracy of this model. I'm going to create some predictions, and I'm going to check out the accuracy score. Accuracy score is 73%. I'm going to look at the confusion matrix. I can look at the results there. Won't dwell too much on that. I'll just go ahead and for the time being, let's just go with the ROC AUC score. And this is the metric we'll use for the remainder of the class. So it's the 76.8% there. So now what I want to cover is how do you tune the tree? Because these parameters I mentioned earlier are sort of arbitrary. Max step of equal to 3, it's sort of arbitrary. So how do you find the optimal parameter value? This will be somewhat repetitive for you because you will have seen a lot of this before, but for this case, there'll be different tuning parameters. So I'm going to create an X and a Y variable, which is going to be based off of my entire data set, not just my trained data set anymore. Y is on my entire data set, not just the trained.
It's going to split it for you when you run.
Yeah, it's going to split it for me, exactly. So I've got that. And so I'm going to check. First of all, I'm just going to do the cross validation ROC AUC for a max step of 3. So I'm initializing my tree here. and then I'm running the cross-val score, and I'm getting 5 cross-val scores. I'm taking the mean of that. So I get a cross-val score of 83, 83.7. So slightly better. So 3 seems to be better than 2. Let's try bumping it up to 10 and see what happens there. So I'm going to do 10. What?
You're crazy.
So 10, and it seemed like it went down a little bit, 80. So you know, how do we do this? Well, I'm going to create a parameter grid, which is just a dictionary where the key is the name of the parameter and the value is the list of values I want that parameter to be tuned over. So here you see a dictionary where max depth is equal to depth range, which is just a list of integers from 1 to 20. So key is max depth, values are a list of integers. And then I also initialize a tree, and then I'm going to instantiate my grid search object, and then I'm going to fit. And you see that the new argument there, the param grid, is just that dictionary that I just defined. I'm going to fit, and you see how this param grid equals max depth, and it went from 0 to 19. So I trained 20 different trees. Or, sorry, 1 to 20. So 19 trees. I'm going to get the average ROC AUC scores, and these are going to be 20 scores because I have 20 models, and I'm getting the average because this is a 5-fold cost validation. And so here's 20 values corresponding to these 20 different trees, and then I'm going to plot the results. And you get this kind of profile. So you've got the accuracy, the ROC AUC metric on the y-axis, and the number of the max depth. Max depth for all of the different trees here. Starting at 1, we're to 19. So based on this kind of diagram, what I would be inclined to do would be to pick the one that gives the best results with the least number of training, with the least number of fitting. And so I would probably pick this one. And as I have a simpler model, this is actually makes my choice easy because it's the best accuracy, and it's a relatively small tree. So then, how do I get that model? Well, there's another attribute of a grid search object that is called best estimator. And so that actually is, surprise, surprise, the decision tree classifier with the max depth equal to 5. All the rest of these are just the default values because I didn't specify anything else. I just specified, I think, random state. I just specified min samples leaf. So this is another value you can tune over. I said you have to have at least 20 samples in the leaf before you can split. If you have 20 or less, then don't split. Don't split that anymore. And you see that show up here, and then you see the max depth equals 5 show up here, indicating this is the result of this grid search. Alternatively, I could just create another tree and specify those parameters that I found, that I discovered from my graph. I won't open up that one, but so that was pretty fast. Any questions about any of the whole process? Fitting and tuning the tree. Yeah.
So for the best equals grid dot best underscore estimate underscore, is the underscore part of syntax, or is it?
Yes. So grid best. The underscore at the end. I think that that's just a convention scikit-learn uses when you're dealing with attributes, because when you do something like this, grid, and you do the tab complete, so you'll notice that you remember how you said like there's attributes and there's functions, attributes and methods. The whether or not it's an attribute or function is not necessarily apparent just from looking at this list. But by putting an underscore there, it makes it easier to tell, just from looking at this, whether it's just a signal for user usability, I guess. Yeah. Any other questions? What is the most confusing part about everything I just said? The most confusing part, or the weirdest part, the most unexpected part? Yes.
You know what's weird?
What is weird? It's not.
This is the first time we've ever actually been able to quantify feature importance to some degree. Why is that so hard for our models? Or why is it so easy for this and harder for other models to display that? But that's interesting because it plays me to this day.
Yeah.
Why can't I quantify feature importance as well as I can just distribute?
Yeah. So that's an interesting question. So first of all, I would say you can quantify importance in a sense when you're looking at linear logistic regression. You can measure the strength of a relationship and the significance of the relationship, which are two separate things. Here you're just looking at it's not a statistical, it's not a parametric thing. It's just looking at the strength of the relationship. But I think what it comes down to is that it's a very simple model. It's just a model that just combines basic Boolean logic. The model can just be explained in terms of basic Boolean logic. And because of that, you can, because of the way it's created, you can get those feature importance scores. I don't know. Cool. So neural networks would be like the extreme other direction.
Yeah.
Like I have no idea whatsoever. But I think even in techniques like PCA, for example, I think there are ways to regain interpretability from principal components. You can do for those of you guys who know what principal components is, it's dimensionality reduction. We're going to cover it next class. Actually, it's not going to cover it. So I don't want to steal your thunder, but one of the things I've seen with principal components analysis is doing like a correlation coefficient matrix, where you have your principal components and you have your explanatory results. So you can have some you can regain some interpretability from. So there are ways to back into these things. Some models it's very hard to, like the neural networks, which is one reason why I never use neural networks. Yeah.
And could you potentially show us how you would tune the leaves in a similar way that you tuned Mesfit for the depth? Would it be a similar process?
Yes, it would be the exact same thing. So if I were to do the leaves, the only thing that would need to change
It's just like leaves
would be instead of max depth equals max depth range, I would do min samples leaf equals whatever I want it to be. But it has to be. It just has to be spelled the same way as And you can do more than one. You don't have to just do one at a time. You can tune over multiple parameters. And actually, this is part of the challenge exercise. I'm really excited about this challenge exercise. There's so many different ways you can go with this. Part of the challenge exercise is see if you can tune over two parameters at the same time. It's possible. It's definitely possible. So, anyways, I saw a hand up over here. Yeah, here.
We went over naive phase. I think I remember it said initially in my head, everything that is supposed to be used for things like many features. Is it all for function features? Is that right?
Yeah.
I'm going to compare it to this and say why is this not better if you can tell the quality of features so easily.
Why is this not better?
Than naive phase.
I wouldn't necessarily just after that. This is better than iBase or vice versa. We would have a case by case comparison.
So you had a data set with a ton of different entries and you were trying to understand what
I would say this is a good technique for that. This is a good technique because one of the this is very automated. It's very automatic in terms of the features that it's choosing. And there's an advantage here that is not present in logistic linear regressions, which is linear regressions are assume this linear functional form whereby each explanatory variable is independent, and then if they're not independent, then you got to do something about that. Maybe include an interaction term, but you got to before the fact you got to put that in the functional form. You got to put I'm going to make these terms interact with each other. There's an interaction. Here, you actually have the interaction term as being created automatically. So this split right here, each split is making the best local split. Sometimes this is called has a greedy nature because what's best for the local split might not be best for the model as a whole. But regardless, it's making the best possible split for this point, for this set of data, which is defined by it's defined by the preceding logical state, preceding logic. So this model is building in, it's a combination of Boolean logic, so it's building in interactions automatically, building in interactions between these different variables. Whereas linear regression, you have to explicitly account for that. You have to programmatically create that. Does that make sense? Or, okay. Okay. Any other questions about this before we move on? Okay. Let's see, what time is it? 2:50. Okay. Great. All right. So for this next topic, we are going to do something a bit different. If you go to the notebooks, first of all, how many of you guys have used IPython Notebook before? Okay, a couple of you guys have. IPython notebooks. What are IPython notebooks? For those of you who used it before, how would you define it? What is it used for?
Embed code and comments and graphics.
Mm-hmm. Yeah. It's a one environment. It's one place. It's like one hub that you can use to combine pictures and rich text and code. You can even use it to run code, but it's a great way to share the results of analysis with other people. Post it on your website, for example. It might be something you might be interested in using for your project once you see it. But I wanted to show you what it looks like, and for this next section, we're actually going to be going through it using an IPython notebook. So the way you start up an IPython notebook is you navigate in your command line to where your IPython notebook is. And so I have created a folder called Notebooks in DAT6, and there's an IPython notebook there. So if you go to your command line, take a moment to go to your command line and just go to the Notebooks folder and type in IPython notebook, capital I, capital P. So just take a moment to do that. I'll give you on the screen just a moment. Just to make sure that everybody's able to follow along. So go to this. Oh, your cursor's stuck.
Oh, do the context of it.
So we'll do- Or you can just add that. You actually don't need this. It's really good if you just do it around the square. What? You just go over to oh, let's come back to that. I'm just going to show it. On file. So you go to the program. We'll begin under this. Oh, okay. Really want to. Anyone having trouble getting it up? Okay. So I'm going to go ahead and launch it. So how does this notebook work, or what does it look like? Here you see what it looks like. You click on the 08 ensembling techniques.ipynb, and you'll see something like this, and you'll see different cells, and you'll see a lot of HTML text there. You'll see some images. If you scroll down further, you'll see some actual code down there. And so this is what's meant by sort of integrating all of these different elements into a single document. How does this work? Well, to be able to run the code, first of all, the code is being stored in the IPython notebook, and that's the file that has the extension ipynb, IPython notebook. And then to execute the code, you also have an IPython kernel being run in the background, and this has to be running in the background for you to be able to use the IPython notebook to execute code, and this is what's taking that code and interpreting it. Okay, so this kernel has to be running in the background for you to actually execute code here, that's sort of how that works. If you want to view somebody's IPython notebook without going through this whole process of starting up your own kernel, you can do that. If you go to IPython notebook viewer, the first hit should be this link here, nbviewer.ipython.org, and you can actually go to somebody's. Let's go to our repository. Let's go to the notebooks, and the notebooks here, and click on this Python file, which is not very interpretable, just looking at the GitHub. But you can take this GitHub link and you can paste it into the NB viewer, and after a few moments, you can actually view the GitHub, the entire notebook here with all of the pictures and the text and the code. You can't run it here, but you can show it here, and you can share it through this. And I believe if you wanted to include like a notebook on your website, like a link to check out some of my work, you could just include a link to a viewer like this. This is sort of a handy tool for just viewing other people's code really quickly without having to start up anything on your own end, or sharing it with other people. Okay? Let's see here. The last thing that I'll say is about IPython notebooks, and this is the reason why I don't really use the IPython notebooks personally. I know a lot; they are very popular, and I see them a lot, and I see a lot of people using them. I don't use them a lot personally because a lot of what I think they're very good for presentation. I don't think they're as good for development. As good tools for development. So when I'm doing development, I almost always use just regular Python files. The reason for that being is that it's much easier to use version control on a .py file than a Python notebook file. There are ways to do version control on Python notebook files, but it's not very easy. And so I almost never do development in Python notebooks. But I wanted to show you what it is so that you're aware of it. Yeah, so any questions about IPython notebooks? I know it's just a very brief introduction. I've got some links for how to use this, and we'll sort of use it together. It's, I think, pretty straightforward to use. But any questions on any of that? All right. So why don't we do this? Why don't we cover the... We'll start covering the ensemble methods. We'll do the basic principles of ensembling, and then we'll take a break, a 10-minute break. Okay, so ensembling methods are all the rage these days, especially on Kaggle competitions, Kaggle forums. What is an ensemble method? The idea, I saw a quote that I liked from the Bible. In abundance of counselors, there is safety. The basic idea behind ensembling is that you take lots of different models and you combine them together. You create lots of different models and you combine them together. And the result is some kind of vote. It's like a committee vote. So that's what ensembling is. Generally, the reason people use ensembling is that it gives them better accuracy than just using single models by themselves. And so that's why you see they're very popular on the Kaggle competitions, where the goal is optimizing for accuracy. So during this section, we're going to be talking about, how do we get the most out of our ensemble? What is the process for creating an ensemble? What are different variations within that? What are different ways to create ensembling models? And then we're going to talk specifically about the random forest ensembling approach. I'll give you the code for that. I also created code for the AdaBoost algorithm, which is another popular ensembling technique that's based on trees. And if we have time, we'll get into AdaBoost, but I'm guessing we probably won't have time. So we'll probably just stick with the ensembles, introduction, and random forests. And then I prepared the lecture material for AdaBoost as well, so you're welcome to look through that as well. So, ensembling. Just to provide some motivation for it, I was going to ask the question, what is your opinion of this question? Given a task, an objective, an initiative in work, which is more effective, an individual or a committee of individuals? And if it depends is your answer, which is the standard consulting answer, then what does it depend upon? Huh? How do you define effective? Okay. So different people maybe come together, have different ideas about what should be done. They have their own agendas. So that could, be less effective, than a single person who just has a clear vision and idea about what needs to be done. Sure.
Does it depend upon whether the answer can be precisely found or whether it's more strategic?
Okay.
Sure. A group would be better with something strategic, whereas if the answer has something there will allow you to
Do you guys like working in committees or no? No. What's that?
It can be stifling if there's not good honesty.
Yeah, definitely. I'm sure I'll have mixed opinions working in committees, especially in Washington, D.C., the home of government bureaucracy. I thought this Dilbert comic was funny. Let's have a little pre-meeting to prepare for your meeting tomorrow. And Dilbert says, whoa, do you think it's safe to jump right into the pre-meeting without planning it? And then next thing you know, his boss is planning the pre-meeting. Okay, let's get this preliminary pre-meeting meeting going. You think you're funny, but you're not. I love this quote. This is so right on. I think typically when we think of committees, we think of just bureaucracy and endless approvals and just competing interests. And so the analogy, taking the analogy of ensembling techniques into the real world and your personal experience may definitely break down for various reasons. But to provide some more concrete motivation for the topic of ensembling, I wanted to point your attention to a study that was conducted by Elder Research, which is a data science consulting company that has done some really interesting work, especially in the federal government space. That example about paper pushing in the Social Security Administration I shared with you guys at the beginning of class, or actually, maybe Sonali shared it. That was a case study from their company. They automated some of these paper processing. They've done a lot of cool stuff in the federal government. But anyways, they did a study where they compared 6 different data sets and 5 different classification models. All these data sets have binary response discrete response classification tasks, and they evaluated different models: decision trees, neural networks, logistic regression, and they measured the error as well. So the lower the error is better. And what they found was sort of interesting, as you can sort of see by all the variants here. When the guy was presenting his results, he said every dog has its day. And what he meant by that was, if you look at the results, every single modeling technique, all 5 of these modeling techniques, were best or second best on at least one of the data sets. So I thought that was sort of interesting. And he was basically saying, it can be very hard to determine beforehand which modeling technique is going to be best for a particular set of data. But what he did next was even more interesting. He took those same data sets, those same classifications tasks, and he created he fit them using an ensemble of models. And the scale is the same on the y-axis for the error, and the data sets are the same. The only thing that's different is that instead of using a single model, now he's using a committee of models. And as you can see, just comparing, and there's 4 different lines for 4 different ways of combining the data together, combining these the output predictions of all these models together, which we'll talk about momentarily. But as you can see from the difference between this first graph and the second graph, the ensembles pretty consistently across the board perform as good, if not better, than the best modeling technique for each data set.
What's advisor perceptron? How are they combined?
That is a reference to something that we'll talk about in a minute. Yep. Okay, so that's sort of the that's the experimental motivation for this topic. I came across this theory, which is based on the binomial probability distribution, called Condorcet's jury theorem. Have you heard of that? Have you guys heard of that? I hadn't heard of it. The past class, one of the students mentioned it to me. He said, "Hey, this sounds like Condorcet's jury theorem would actually provide some theoretical proof for why an ensemble of models, given certain conditions, given certain assumptions, would be better than a single model by itself." And I actually explore that topic here. I won't go into that now, but suffice to say, given certain conditions being met, The most important of which being that the models be independent of each other. The models be different from one another. Having a diverse, you can think of it back to the committee example. If everyone on your committee has the exact same background, everyone in your committee is going to have the exact same strengths and weaknesses, and you're not really going to get, the benefit of having a group of people come together. But if you have a group of people coming together and they're crystal clear on what their objective is, and they all come to the table with a different set of strengths and skills, then you're going to maximize the fact that you have a group of people coming together. Whereas if everybody comes to the table with the exact same set of strengths and weaknesses, then it's not going to be as effective. That's sort of the analogy of independence. But assuming independence between models, you see you'll see a consistent decrease. If you look at the probability of accuracy with a vote, a committee of models, versus just a single model. But I'll just skip over that in the interest of time. So you were asking about the advisor perceptor, different ways of combining predictors. Basically, the two steps for creating ensemble models, I want to be really clear on this. Ensembling and random forest are not the same thing. Ensembling is a reference to something you can do with models. It's not specific to a random forest. Random forest is a specific instance of an ensemble technique. Ensembling is basically two things. You create predictive models, and then you combine them together. That's what ensembling is. In terms of creating predictive models, the way to maximize the benefit of getting the accuracy of your ensemble is to have your models different from one another. Okay? The way to get your model different from one another, there's lots of different ways to do that. You can train your model on different subsets of the data. You can train your model on different subsets of the features. You can train your model using different techniques. You can train your model using the same technique, the same data, the same features, but different treating parameter values. There's lots of different ways to do this. But the basic idea is you want your models to be different from one another. Then the second part is combining the predictions. Now there's lots of different ways to combine predictions. A lot of times when you do a classification, it's just majority votes. You have an odd number of models, majority vote. You can average the results together for a continuous output. Also for a discrete output, you can average them together. The third method, which goes back to the advisor perceptron question you had, is something called stacking. This one took me a while to get. Let me write this one out. So let's say that we have 3 models, and for the sake of argument, we're gonna say we've got a KNN, a logistic, and a decision tree. After fitting these models on a certain set of data, each one will spit out a prediction in terms of, let's say it's a binary class problem. And this one predicts 0, this one predicts 0, this one predicts 1. This one predicts 1, this one predicts 1, this one predicts 1. This one predicts 1, this one predicts 0, this one predicts 1. Etc., etc. What you can do, as I've shown here, is to combine the predictions in a single data frame, a single array, where each column is the prediction from one of the models that you've created. So stacking, and then in addition to this, you can add in the truth labels. And here, this one really was a 1, so the decision tree got it right, and the KNN and logistic got it wrong. This one was a 1, all 3 of them got it right. This one was a 1 as well, or let's say this one was a 0. So you got 0, 1, and 1, and this one, the decision tree and the KNN got it right. So you can combine your data like this, and now, this is the part, crazy part. You can train a model using these as features and this as your response.
Let me just put that up here.
Any questions about that? Yeah.
Good model.
Sorry?
What model do you use?
Well, so you could use any model that has any model that is a classification model. So if you have a classification cast, you could use the K&N, you could use logistic, you can use a decision tree. A lot of times logistic is actually used for this. This is a very common, just sort of conventional that logistic is used for stacking. But the advisor perceptron is another one. I believe that's a variant of artificial neural network. But yeah, so you can train a model on the models, to get your prediction, and you can use that process to generate your predictions. Yes.
So you're saying this is separate. I'm not like adding these columns to my original data set and using them. This is a separate prediction I'm using. That's determine which model or which combination of models I use for each row.
Mm-hmm. Yes.
So it sounds like you need to tune each individual X feature as best as you possibly think, or you train it, or you tune it as best as you think that you can before you do the stacking.
Yeah.
Revision.
Yeah, you can do that. Yeah. Yeah.
Or you would want to, right?
Yeah. Yeah, what do you think? So one thing I want to make a note of here. I want to come back to. We talked about one of the strengths and weaknesses of decision trees is that they are high variance. What does this mean? This means if you replicate the training process over different subsets of the data, you're likely to get different results, very different results. They're unstable, is another way to say. This is one of the aspects of decision trees that make them so suitable for ensemble. Because you get lots of different, the idea behind random forest, which we'll go into right now, is that it combines multiple decision trees together. Decision trees that are different from one another. So if you understand how to make a decision tree, the random forest is actually only a couple steps in addition to that.
How is that high variance also the strength?
Good question. So the high variance means that for any particular region and for any particular subset of data, the models are going to be different for that particular subset. So when you have you basically have models that are very different from each other. They're very decorrelated from one another. And when they're decorrelated from each other, then when you combine them together, then you get the better result. But if they're all very similar to each other, you don't get an added benefit. I don't know, Sanaa, would you have anything to add?
To the benefits of high variance,
Or in answer to the question, why is high variance a strength for decision trees and ensembling?
I guess, that's pretty much what I would have said. You have a lot of different things doing. It's like if your team, if everyone's doing the same thing on the team, nothing's getting done. But if everyone brings something to the table and you combine it, it's kind of like some more analogy.
Yeah.
Is if you have one linear model and just keeps doing the same thing over and over again. Or if you have a decision tree, and each time the decision tree is doing something different, put them all together, you have a stronger model usually.
One analogy that someone shared is that when you're trying to make inferences about a population, you're doing a survey. As you increase your survey sample size, you get better and better representation. You get closer and closer to truth. It might start to taper off in terms of how much benefit you get from adding more and more samples. But up to a point, you get a better representation of the truth as you get more samples. Another analogy that I've seen is, let's say you are trying to, let's see where can I draw here. Let's say you're trying to fit data, and the data looks like this. And that's like the true line is, something along along this line, and you see some like data like this, and you're fitting, for one subset, and you're fitting lots of these different decision trees on here. And you've got some decision trees that are overestimating, and you've got some decision trees, and decision tree, it wouldn't look like this, but you've got some models that are overestimating, you've got some models that are underestimating, but you've got a lot of models that are getting pretty close. And so when you average them together, there's a couple models that are overestimating, which are going to cancel out with a couple models that are underestimating. And as long as your model is better than random, the overall result is going to be closer to the truth than just a single model.
Also, the model with high variance, you have a better chance of capturing outliers. Because if the model is known to have that drawing, the models that are over and underestimating,
Mm-hmm.
you're better at capturing some of the data points that are farther away from that average line.
Yeah.
That's not the purpose, but it has been known to capture outliers better than a low variance model.
So
It might be.
if you have an n of a bunch of outliers, instead of decision trees, then it's going to make a decision tree based off of the outliers.
It wouldn't be based on, every model is based on every single data point that you give it, but in my experience in production, decision trees are better at capturing, like predicting outliers, just because in a linear regression, you have your basket line, and that's more sticks. Am I making sense? I'm sorry, I don't want to.
I mean, it's interesting you say the thing about the outliers. In my, one of the things that I would say about decision trees, maybe I'm just not understanding I probably just not understand what you're saying, but one of the benefits of decision trees that we haven't talked about is like how they tend to be robust to outliers because you're just making these binary splits, so they're not going to be thrown off. Like regression to the mean is called like regression to the mean for a reason, and so because of that, it is going to be thrown off. It can be thrown off by outliers.
Yeah.
It is sensitive to outliers, whereas decision trees aren't because you're just making that binary split.
We're saying the same thing.
Oh, okay.
I think we are.
Okay.
They're not gonna actually
Yeah. Yeah, so I don't know if that helps with your question, or if I probably need to think of a better way of explaining this. So your question was, why does high variance models help give a better ensemble? Is that correct?
Well, I was just asking, like, why for decision tree, if you introduce it, you said high variance, it's like, it's the biggest strength, also the biggest weakness, but.
It's more of it's a weakness that you're just looking at the decision tree in itself,
Right.
because you've got to tell it, you've got to prove it, you've got to make it stop going at a certain point. You can't just use that out of the box. But when you are combining lots of them together, and you're averaging all the results together, then it helps because you get lots of different trees. And averaging over all of your trees, as long as they're better than that, like as long as they're better than just random guessing, which they should be. The extreme, the extremes average out, and you're left with a better fix in aggregate. Good question. Okay, let's go ahead and take a 10-minute break, and we'll come back at 3:35. Get some coffee, get some Red Bull, which we need to do.